Hi, this is Brandon Baines in the math department at Lipscomb University. Here to talk to you today about the fundamental counting principle. In this app, you'll learn how to solve counting problems using the fundamental counting principle. What we mean by counting problems is scenarios where we want to count the total number of outcomes or the total number of collections. That may sound trivial. We know how to count, but sometimes we want to count things that are rather large. And so what we're going to learn in the first part of App 7 are ways to count things using methods that even if the number of things is very large, we still have a manageable way of counting it. So the fundamental counting principle, it allows us to consider scenarios where we have several events that occur in succession, and we want to count the number of ways all of those different events could occur together. So, for example, if James owns 3 pairs of shoes, 5 pairs of pants, and 4 shirts, and he wants to create an outfit consisting of a pair of shoes, a pair of pants, and a shirt, the fundamental counting principle is going to provide us a way to consider the way James could string those shoes, pants, and shirts together. We might begin by thinking about that scenario and thinking about how we could create an outfit for James. We could count those. We have maybe James owns a pair of Nikes, and maybe one of the 5 pairs of pants are khakis, and one of his 4 shirts. So we could create an outfit of his Nike shoes, his khaki pants, and one of his 4 shirts. But he could pair the Nike shoes and the khakis with any of the other 4 shirts, and so that provides many more outfits that he could create. And then, of course, he could change the pair of pants. He could change the shoes. And so it turns out there's quite a few ways that James can create this outfit. So listing them would work, but it's not going to be incredibly efficient. There are other examples that will allow us to use this fundamental counting principle. Those are things like passwords, where we have 8-digit passwords, or we've all created passwords at this point where we have different requirements. We might want to count how many possible passwords there are. We also might consider if we are given a multiple choice test, we might be interested in knowing the number of ways that we could answer all of those questions. So the fundamental counting principle says the number of ways in which a series of successive events can occur is found by multiplying the number of ways each event can occur. So in our previous example, the counting principle would say that there are 3 times 5 times 4, which is 60 possible outfits for James. We'll take a look back and see where those numbers come from. So James has 3 pairs of shoes, 5 pairs of pants, and 4 shirts. So when he wants to choose one of each of those, then the counting principle says that we'll multiply the number of shoes he has by the number of pants he has by the number of shirts, and that's all the ways you could pair those 3 events together. Let's consider an 8-digit password that consists of only numerals from 0 to 9. And we want to know how many possible passwords can be created. So in this password problem, each digit of our password will be considered an event as we think about the fundamental counting principle. So in this problem, we have 8 events then, and each of those events can occur in 10 different ways because we're selecting from the numerals from 0 to 9. So the number of possible passwords is 10 times 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 10, or with exponent notation would be 10 to the 8th. And when we multiply all that out, we get 100 million different passwords. Why do most passwords have requirements that include other characters, like letters, symbols? That'd be a question for you to think about that you may come back to later. Let's take a look at another example. At a local meat and 3, there are 2 daily meat offerings and 5 daily sides. How many possible orders of a meat and 3 sides are offered if, part A, all of the sides must be different, and part B, the sides can be the same? For example, you can order a double order of mashed potatoes or even a triple order of mashed potatoes if you like. Well, part A, where we were forced to choose 3 different sides, we still have 4 events. We have the event of choosing a meat, the event of choosing our first side, the event of choosing the second side, and the third side. So the counting principle would tell us just to multiply the number of ways those can occur together, and that would give us our total possible number of outcomes. Well, there are two meats each day on our at our meat and 3, so there's 2 choices there. There are 5 sides, so for our first side we have 5 choices. But keep in mind, in part A, we can't duplicate a side, so the choice of the second side will only have 4 options. There are only 4 ways you can choose the second side because you've already selected one of the sides from the 5. And to select the third side, there are now only 3 sides remaining because you've picked 2 sides already. Multiplying all those together, we have 120 possible orders of a meat and 3 sides. In part B, we're allowed to duplicate sides. And so in that case, when we consider our 4 events, there's still 2 ways that we can select a meat. And there are 5 ways to select the first side. But now, since we can duplicate, there are still 5 ways to select the second side. And there are still 5 ways to select the third side. So using the fundamental counting principle, we have 2 times 5 times 5 times 5. It's 250 possible orders of a meat and 3 sides.